Welcome to your first video covering the information from your Chemistry 1 review packet. Make sure and put your name on the front cover. So in my case, Miss O'Brien. This packet will go through all the information you should have learned in Chemistry 1. If there are things you struggle with or don't remember in here, this gives you an idea of where you're going to need to work very hard coming into the new year. You will have a test over the basic knowledge in this packet in the first week of school. Let's begin with the concepts of precision and accuracy, and the fact that they are not actually the same, hence the use of the word versus. So this is precision versus accuracy. Now, colloquially we use these two interchangeably, but that's not actually the correct method of using these words. Accuracy refers to how close a measured value agrees with the accepted or goal value. Now, as I go through these packets, I want to make sure you write down anything that I write down. Now, that is the minimum of what's required in these packets. If you want to add down anything I say or anything that reminds you of how you learned this originally, this will be a great resource for you throughout the year of AP Chemistry. So if accuracy is how close a measured value is to the goal value, then precision is how closely related individual measurements agree with each other. You probably learned to relate accuracy versus precision visually using a target. So to say something is accurate and precise means we're hitting the goal. The goal is, of course, the center of the target. If you are precise but not accurate, well, your data points are closely related. They're all close to one another. This is not accurate because we are not close to the goal. You can be accurate, meaning you're close to the goal, especially if you were to average out all of your different data points. All of these average to about being accurate. But you're not precise. You're not hitting the same exact point over and over again. You're hitting all over an accurate range. Finally, in this last example, you are inaccurate because although you have one point in the center, the rest of them aren't going to average out to being accurate. Instead, the rest of your data points seem to be precise at this point over here. The fact that the rest of the data points are all right here actually makes this appear to be a random data point that happened to end up in the accurate range. Now, both of these are more complicated concepts that I don't expect you to fully understand, but make sure you do understand the basics here. The basics of accuracy and precision are very important when we're dealing with lab work. Precision is evident in your lab work whenever you're able to measure something to a large number of decimal places. So let's look at the examples below. If we were to compare a beaker, a burette, and a graduated cylinder based off of their accuracy and precision, for a beaker, if I was to measure this blue, let's say it's a liquid in there, the best I could say that this could measure is we know we're above 45, close to the 50 part, so I would say it's about 47 milliliters. Notice the plus or minus 1 milliliter. That's how precise this glassware is able to measure. Notice, a beaker is not able to be very precise because it doesn't have very many decimal places. It also can't be very accurate because if I said my goal was 47 milliliters, can you say that this liquid was exactly 47? No, it has too much difference in its possibilities. So a beaker is really only used to carry liquids. We'll be talking about that a lot throughout this year. Never use a beaker to make a measurement. Now a burette is a piece of glassware you may not have used before. A burette is very long, it stands on a stand, and has a point at the end with a little nozzle that you twist. I know, I'm a great artist. So here's my little stand, has a little clamp, and it goes on a ring stand. And we use it to add liquids to a beaker or a flask. But what I wanted you to notice is that the numbers go from 20 up here to 21 because we measure the liquid as it slowly empties down. So your numbers go in this direction. So in reading this, a good volume reading would be 20.1, 0.2, 0.3, but notice I can still tell the difference between how far it is between 20.3 and 20.4. Therefore, I would say this is about 20.37. Because of the fact that a burette can measure out to 2 decimal places, 0.01, the burette is the most precise of all 3 volume measuring devices because it has more numbers past the decimal, which increases the repeatability of the numbers measured. What that means, the repeatability, right, precision, is if I tried to fill a liquid in this beaker to around 47 over and over again, the likelihood of me being in the exact same point is smaller and smaller. However, because I am able to measure out all the way out to 2 decimal places, I could get this exact same measurement multiple times and be very precise. Now, a graduated cylinder is, of course, the most common way we measure volume because a burette is a complicated measuring system, whereas a graduated cylinder is quite easy. Reading this graduated cylinder, it would be 36.5 milliliters, and notice that's plus or minus 0.1. It has a range of 0.1 milliliters, which is still pretty precise. Now for significant digits, which we call sig figs, which stands for significant figures. Significant figures are the numbers inside a measurement that represents the precision that was taken in that measurement. Students sometimes struggle with sig figs, so I've made sure to simplify this down into 2 basic rules. You must have these 2 rules memorized because sig figs are very important throughout this entire year. The first rule has a very major typo. The difference in the 2 rules are if there is a decimal or if there is not a decimal. So this first rule, if there is no decimal, then we start from the right. Okay? Look at the number as a whole and start from the right. So, right. So we start from the right and we go to the first whole number. A 0 is not a whole number, so we don't count that first 0. The 6 is going to be my first whole number, and then we count every number after that. A 0 is a number, it's just not a whole number. Every number after that 6, which gives me a total of 4 sig figs. So for a quick example, if I had 1010, notice it does not have a decimal. Therefore, we would start on the right. We would not count this first 0 as our first whole number. That 1 would be our first whole number, and all 3 of these would count to give me 3 sig figs. So what if we do have a decimal? Well, if we do have a decimal, so if yes for a decimal, then we start from the left. Okay, start from over here. And once again, the rest of the rule is the same. Go to the first whole number, zeros don't count, and count every number after that, zeros do. So go to the first whole number, none of these zeros count, but that 5 does, and every number after that. So total here we have 3 sig figs. So if I take that same example from before, 1010, and I put the decimal place anywhere in the number, it doesn't matter where I put it. As long as there is a decimal somewhere in the number, now I would start from the left, and I would go to the first whole number, which would be the 1, and count every number after that. So in this example, I actually have 4 sig figs. So the placement of decimals is very important. And that's what leads us into our next 2 rules when we are multiplying and dividing or adding and subtracting using those sig figs. So when you're multiplying and dividing using sig figs, we're going to use the least number of sig figs. So in this example where I have these 3 numbers being multiplied, this is the answer that your calculator would give you. We need to identify the amount of sig figs in each of the calculated numbers in order to find out the sig figs that should go in your answer. So in this first example, Notice I do have a decimal place, so I'm going to start from the left, start at the first whole number, and I have 4 total. I do have a decimal place, start from the left, first whole number, 3 total. And I do have a decimal place, start from the left, first whole number, 4 total. Therefore, 3.10 has the least number of sig figs, having only 3 sig figs. Therefore, my answer can only have 3 sig figs. Your answer can only be as precise as your least precise calculation. So 3.10 having only 3 significant figures means my answer can only have 3 significant figures. So 5,946 blah 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 rounded to 3 sig figs would be 5,950 because that 6 would round the 4. Okay. Now be careful and do not put 595 as your answer. If you have $5,946 and somebody's rounding it for significant figures and says now you have $595, you'd see the mistake. You cannot change the size of the number. What you are changing is how precise it is. You're changing its significant figures only. Now when you're adding and subtracting using significant figures, in this case what we care about is the least number of decimal places because the precision is already decided by the decimal places. You don't need to look at the significant figures for adding and subtracting. So for 3.76, I have 2 decimal places. For 14.83, 2 decimal places. And for 2.1, I have 1 decimal place. So 2.1 has the least number of decimal places, so 20.69 needs to be rounded to 1 decimal place, which would of course give me 20.7. Make sure you understand the rules of significant figures and multiply, dividing, adding, and subtracting using them. This will be crucial through all of our calculations for the entire year. Speaking of our calculations for the entire year, we use a lot of very large numbers, so scientific notation will be your friend in this class. There are 3 parts in scientific notation. We have the coefficient, the exponent, and the base. The exponent must show the number of decimal places. The decimal needs to be moved. So if we move it to the right, we have a positive exponent, and if we're moving it to the left, we have a negative exponent. So for example, 6.03 times 10 to the 7th, we're moving the decimal place to the right. And to change 3.670 times 10 to the negative 3, we would need to move it to the left. So we have 3670, 1, 2, 3. That's where our decimal place will go. And we put 0, so 0.003670, which is our goal. So this would be moving to the left. If you are unfamiliar with putting scientific notation into your calculator, you need to get familiar with it. The instructions are here below. Instead of an EE button, you may just have an E on top of another button. It depends on what type of calculator you're using. You can always just Google whatever calculator you're using with the word scientific notation, and you can find a video to show you. Now for the 2% calculations that are very important for lab, percent error and percent yield. Percent error is a way of determining the accuracy of a measurement. So this calculation is going to be the experimental subtracted by the literature divided by the literature value times 100. Now if you don't like the term of literature value, think of that as your established or your expected value. So we have our experimental value minus the literature or the given value, what were you supposed to get, over the expected over the literature. Whichever terms you like best for this relationship, you can place them in there. Times 100 because it is a percent calculation. So the literature value is the known value of the measurement. Now, in percent error, our goal in even doing this calculation is to get a 0% error. If you're doing a lab, you don't want to have any error. You want a 0% error. Okay, now let's make a little dividing line. So what is percent yield then? Well, percent yield is going to be the comparison of the actual amount of product versus the amount of product you calculated. So the formula for percent yield is the actual amount of product, or how about your lab amount of product, over your calculated amount of product. Now when we say calculated, our calculations are from stoichiometry. So we used a calculation to say, well, if I start with this amount, how much should I get as an amount of product in a, perfect world? So our goal for percent yield, well, what would we want to gain as our yield? Well, we want 100% yield. And that shows you the difference in how they're calculated. By using your experimental minus the literature divided by the literature, you should get closer to a 0. But by using a lab amount divided by a calculated amount, you should be closer to 100%. Now for graphing. We have the independent and dependent variable, and you need to make sure you understand both of these. Your independent variable is the variable that you manipulate. And it's always plotted on the x-axis. And the dependent variable is the dependent. It is the thing that depends on the variable that was changed, on the independent variable. And it is always plotted on the y-axis. You may have learned this as dry mix. Dry meaning dependent, R meaning responds, and it belongs on the y-axis. So the dependent responds, and it goes on the y-axis. For mix, the M stands for manipulated, I stands for independent, and X stands for x-axis. Another way this can be represented is like this. The D is, of course, the dependent, and it is on the y-axis. The I is independent, and it is on the x-axis. I realize that this is probably review for most of you, as you are juniors and seniors in high school, and you've finished Algebra 1 geometry, and you're usually through with Algebra 2 or just now starting Algebra 2 at this point. So we have a quick example below of how you would use a graph with the science involved. So for density, for instance, density is going to be our slope because the calculation for density is mass over volume. Well, when we look at our graph, our slope is always our rise over our run, or our y over our x, and therefore that would be our mass over our volume. So using this graph, we can find our density at any point along this sample. And notice that the density is the slope, so density is always the same for a sample. And you would be able to calculate your density based off the math in this graph. Chemical and physical changes. A physical change is a change in physical properties such as size or shape or state of matter. So it's going to be a change in a physical property. Part of it is bonds do not break. So our chemical formula, such as for salt, NaCl, if you grind up salt, that's a physical change, but its chemical formula is going to stay the same. Stays the same. Some examples of a physical change would be if we take water through 3 states of matter. If we start with a solid, we add heat, it becomes a liquid. We add more heat, it becomes a gas. Now, in doing all of these, the formula is always H2O, but the size, shape, and state of matter changes. The arrangement of the molecules in a solid, a liquid, and a gas are all different. Now, the size of the molecules are the same, but actually the arrangement of a solid water versus the arrangement of liquid water, the solid is larger. That's why if you put a soda can in the freezer, it'll actually explode, because as the water in it solidifies, it actually expands in shape. Now, another example of this would be a mixture. If I was to mix sugar and water, that would be a physical change. Mixing the two together, the size of the sugar, if I put a whole sugar cube, it might go from a large size to a smaller size, but the actual chemical formula of the sugar, C6H12O6, and the water, H2O, these aren't going to change in mixing them. Now, a chemical change is any change that results in the formation of a new chemical substance. Okay. So our chemical formulas change, right? Now, we're going to be using the symbol of the triangle for change a lot throughout this course, so I'm just going to put this here as a little reminder. So in this example up here, we added heat to water, and heat makes the water go through its changes of state. But if we add electricity to water, water actually has a different reaction. When you add electricity to water, it goes through electrolysis and creates H2 gas and O2 gas. Now, in case you've forgotten how to balance a reaction, we'll go through that later, but balancing this, it'd be 2 H2Os makes 2 H2s and 1 O2. So this would be if we added electricity. You can also take a sugar cube and burn it. So if I was to burn sugar, this would be a combustion reaction. We'll talk about that later in this packet. So if I take that C6H12O6 and I burn it, meaning I use oxygen, then I would produce CO2 and H2O. Let's get that O on there. Balanced out, I would have 5 O2s, 6 CO2s, and 6 H2Os. Notice that in these chemical changes, new compounds, new substances have been formed, and these chemical formulas have changed. Now we use two different distinctions for identifying types of properties. Now all that a property is a description of something. And we have extensive properties and intensive properties. An extensive property is a description that depends on the amount of substance present. So if we were to stick to our H2O example and say I have a lot of water or a little amount of water, there will be a difference in mass, length, or volume. Oppositely, an intensive property is a description that is independent of the amount of substance present. So for water, if we're talking about pure water, the color of pure water is always the same. The boiling point, the freezing point, and the density, these are always the same. It doesn't matter if I have a lake, a river, or a drop of water. Of pure water, the color, the boiling point, and the density will always be the same. The density is one that people struggle with because it has to do with mass and volume, but looking at that graph from the previous page, we talked about the fact it was also just the slope because it's this constant ratio of mass per volume. So this relationship of mass and volume will be the same no matter how much you have. So the density of water is always about 1. There are many more intensive properties than there are extensive properties. Now on to classifying matter. Reminder that matter is anything that takes up space and has mass, which pretty much describes everything around you. Air, everything you touch, everything you see and interact with. So that's a very wide category of things, so we need to classify that matter. Matter is first divided into groups based on whether or not it is a mixture or a pure substance. So a mixture would be if you look at a vial. So in this case, all of these examples are going to be if I gave you a vial of matter and I wanted you to classify it, how would you do so? So if you looked at the vial and it had variable composition, and a sample of this material is not uniform and different samples could be different, such as if I gave you dirt. Now I can give you dirt from all over. I can give you red dirt, black dirt, any kind of dirt I want, and we all call that dirt, but it is a mixture. Not all dirts are the same. Whereas if the contents of the vial have a definite composition, it always looks the same. Every sample of that exact substance is always the same, such as pure water, then it is a pure substance, hence the term pure. We further break down mixtures into homogeneous mixtures and heterogeneous mixtures. These are going to be based on whether or not it is uniform throughout, or if it varies in composition or traits from one part to another. Both of these terms use the prefixes that you should be used to by now, homo meaning same, hetero meaning different. So if homogeneous mixture, it looks the same throughout. Heterogeneous mixture, it looks different, hetero different. Now heterogeneous and homogeneous mixtures can be further broken down, and that's what this information is here.
However, I don't expect you to know this yet. This isn't something we covered in Chem 1, but we will be covering this later in the year. I decided to include it here in case you're looking through later on throughout the year when you're studying for the AP test. It's a great way to bring all this information together. Now, what you did learn in Chem 1 was the further breakdown of pure substances. Pure substances are further broken down into elements and compounds. So if I was to look at that vial and I've already decided it's a pure substance, then I look at it and see, is it a single type of atom, in which case I would call it an element, or is it made up of two or more atoms chemically combined, and I would call it a compound. So if you look at this visual representation of this breakdown, it also includes some examples down here at the bottom. So for all of the mixtures, notice there are different types of salt water, different air, different chocolate chip cookies, and different soils. That's why they're mixtures. Whereas for our pure substances, oxygen is always O2. Carbon is always carbon. Water is always H2O, and sodium chloride is always NaCl. You're always going to find them in this ratio of atoms and elements, and they will always be in this certain composition. That's what makes them a pure substance. Now let's use a solubility graph to talk about the three types of solutions. Just a quick reminder of what a solution is. If I had a beaker with a liquid inside of it, this would be my solvent because it will dissolve my solute. Whenever you were to put into the solvent, that's what is dissolved. Solvent does the dissolving, and that's what creates your solution. So I have my three types of solutions. I have a supersaturated, a saturated, and a unsaturated solution. First, let's fix a couple typos on this page. This should be solute, and this should be solute. So let's go through the three types of solutions. Let's start with the unsaturated solution. And for each one of these examples, let's imagine that my solute is NaCl and my solvent is H2O. You've probably mixed salt and water before. So for an unsaturated solution, I've added a little bit of sodium chloride or salt to water, but I can add more. More solute can be dissolved in the solution. For a saturated solution, I continue to add salt until I get to the max or all the solute that a solvent can hold. So I've added salt and I've added salt until I can't mix any more salt in. That's whenever I'm at a saturated level. So supersaturated, well, this super should give you a hint. I actually hold more solute than it would normally under given conditions. In order to do this one, you need to add heat and stir for many, many hours. Because what you're doing is you're adding enough energy to actually add more solute to the solution. So a supersaturated solution has to be made under very special conditions. So knowing these three terms now, let's identify where they would be placed on this solubility graph. So if I have temperature and solubility. So if I'm looking at NaNO3 and I'm trying to decide at what point is my solution either unsaturated, saturated, or supersaturated. Well, for unsaturated, I can add more solute, which means my solubility can still increase, which would be A. Notice when I'm below the line of solubility, I can still dissolve more solute before I've reached this line of solubility. So for my unsaturated solution, that is A. So for my saturated solution, I've reached the maximum point of solubility. So my maximum point of solubility would be on the line, and this would be B. So notice this random point that's way above the line of solubility. The only way we could be this far above the line of solubility is if we are supersaturated. This solution was made using a lab with adding in heat and stirring for many, many hours. So this would be C, our supersaturated solution. Now for the calculations involved with solutions. We have molarity and dilution are the two you'll be using most of the time. Percent by volume and percent by mass should be logical because they're just a percent problem. Percents are always whatever part you're interested in divided by the whole. That's why if I give your grade as a percent, well, how many points did you get? What was your part out of the whole, the total amount? So times 100. But these two, molarity and dilution, you'll be using these on mostly a daily basis when we're dealing with solutions, which most of chemistry does. For molarity, molarity was our moles of solute divided by our liters of solution. So molarity is always moles per liter. For dilution, that's when you're taking one solution and you're making it into a diluted solution. If you're taking a concentrated juice and you're adding water, you are diluting it. So you look at the starting molarity, molarity is moles per liter, and the starting volume, and you compare it to the final molarity and the final volume. You're always going to be looking for one of the missing variables. By this point in your science career, I expect you to know the phases that substances go through: solid, liquid, gas, and sometimes plasma. Now for this course, make sure you also know the terms for each of these changes and phases. So I'll start with a solid. Going from a solid to a liquid is melting. Going from a liquid to a gas is vaporization. Or boiling. You need to know all of these terms because in different AP questions they may use vaporization or boiling, and you need to understand that they're talking about going from a liquid to a gas. Then going from a gas to a plasma, this is ionization. All of these should be logical. Going from a solid to a liquid, we know that that's melting. Going from a liquid to a gas, well, we're making a vapor, so it's vaporization, or boiling, when you're boiling water. Ionization is going from a gas to a plasma. A plasma is just the creation of pure ions. This I don't expect you to know thoroughly. I just decided to include it now. But make sure you know everything in this box. So if I was to go in the opposite direction, if I start with a plasma and I'm going to a gas, that's de-ionization. Then going from a gas to a liquid is condensation. That gas is condensing into a liquid form. Then going from a liquid to a solid is fusion or freezing. Those liquid molecules are actually so compacted that they are now fused beside each other, hence fusion. Now sometimes we skip a step. Sometimes we go from a solid to a gas. We see this a lot with dry ice. So going from a solid to a gas is called sublimation. Oppositely, going from a gas to a solid, skipping the liquid phase, is deposition, where the gas molecules are actually depositing onto a solid and becoming a solid. Now, as a reminder, the way to change phases is the addition or loss of thermal energy. If I take ice and I add thermal energy, you hold it in your hand, you add your heat, it'll go to a liquid. Then if you were to add more heat, let's say you put that liquid on a stove, you can go to a gas. If you add a lot more heat, you can get to a plasma. Going in the opposite direction, if I have plasma, I take away heat, I go to a gas, to a liquid, and finally to a solid. So for a visual representation of each of these, we have a solid, a liquid, and a gas. So in this solid, notice how I have a rigid structure. They're not moving past each other, they're stuck in their place. Now don't forget that these molecules are still moving, they're just vibrating in place. If an atom was to stop moving, its electrons would stop moving and the atom would therefore collapse. So they are moving, but they're just moving in place. They can't move from this arrangement. In a liquid, they slide past one another. And in a gas, they're ricocheting off one another, ricocheting off the walls. So we just said that in order to do a phase change, we must add or remove thermal energy. So when I'm talking about thermal energy, I'm talking about heat. And a big problem that students have is they have a misconception of heat and temperature. So we're going to look at heat versus temperature real quick. So if I was to have a stove, my little stove, with a pot of boiling water. Where is the heat and where is the temperature in this picture? Well, the heat is the actual energy transfer happening going from my energy coil on my stove into the pot, then from the pot into the water, which heats up those water molecules, having it go through vaporization or boiling, and those water molecules come out as gas molecules. So this is a transfer of heat energy because heat is a energy. But temperature is just a measurement. What temperature does is it measures the speed at which the molecules are moving. So this is the average speed of molecules. And we measure in degrees of hotness. So if I have my thermometer and I stick my thermometer inside the water that is in the pan, these molecules will be moving at a certain speed. And I can get the temperature of the water. I can also get the temperature of the gas. These molecules, these gas molecules, are going to be moving much quicker than these water molecules. Therefore, the temperature of the gas would be higher than the temperature of the water. We're just measuring the average speed of the molecules. So heat energy, also called thermal energy, this is a type of kinetic energy. So it's an energy of motion, and that is a quantity of hotness. We're going to be measuring this in joules. In my diagram, heat energy would be these waves of heat, the actual energy flowing through, whereas temperature is just the device that's being used to measure the speed at which those molecules go now that they've had more energy added to them. So let's look at the heating curve of water. So what a heating curve is it compares the time to the temperature. So if I was to start with my solid down here, because it's with water, so below zero we're at a solid. And then once I go above zero, I'm in a liquid phase where the molecules are flowing past one another. And then once I'm above 100 degrees Celsius, then I'm in a gaseous phase where they're free floating all over. Just like in this picture above, if I was to start with ice cubes here, I'd have ice, then water, and then gas flowing out. So we have solid, liquid, and gas. But notice these flat parts or these plateaus on this heating curve. If you look at the time, going from a solid to a liquid, it doesn't happen instantaneously. There's actually this time change in which I stay at 0 degrees Celsius and I'm not officially a solid or a liquid. I'm in an in-between. So these are these phase changes. And let's add those on here. So going from a solid to a liquid, that was melting. Going from a liquid to a gas, vaporization. Going from a gas to a liquid, condensation. And going from a liquid to a solid, fusion or freezing. So going in this direction, we are adding thermal energy or heat, same thing. And therefore we go through melting and vaporization. Now what that energy is doing is visual with the temperature. So notice my temperature is increasing with the increasing of thermal energy, but during these phase changes, my temperature doesn't change because the thermal energy is no longer increasing the speed of the molecules. So when I'm in a solid, when I'm in a liquid, and when I'm in a gas, and I'm adding energy, the only thing that happens is I have an increase in speed. However, during a phase change, at the boiling point and freezing point, here and here, that heat is no longer increasing the speed. So at a phase change, let's put a little key at the bottom. Phase change. Heat breaks IMFs, intermolecular forces, those things that hold the molecules near each other. So at these points, you need to understand that melting, fusion, vaporization, and condensation is happening, and you need to understand the difference between heat and temperature. Really understanding the concepts of what's happening to the molecules here, of these breaking of IMFs, is what we'll be discussing this year, how we're getting more in depth with the difference between heat and temperature. Now we also have phase change diagrams, which instead of comparing temperature and heat, they compare temperature and pressure. So for a certain compound or molecule, they each have the solid, liquid, and gas phase. So solid, liquid, gas. And for each element or compound, at a certain pressure and temperature, it will either be a solid, liquid, or gas. So once again, we have our phase change depicted going from a solid to a liquid, then a liquid to a gas, or from a gas to a liquid, or a liquid to a solid. And this is where that deposition and sublimation occur, is across this line, going from a solid to a gas, that's sublimation, and going from a gas to a solid is the deposition. We will not spend a lot of time on phase change diagrams, but it might help you give a visual representation of why something is a solid, liquid, or a gas, and it's based off of its current temperature and pressure. Now for a quick review over the history of the atomic theory. The main ones you'll need to know are Democritus, Dalton, Thomson, Rutherford, Bohr, and Chadwick. So Democritus was the one in ancient Greek times. He came up with the concept that if you took something and you kept trying to break it down, take a piece of paper, kept splitting it in half, eventually you're going to hit something that's uncuttable, undivisible, which in Greek, uncuttable, is the word atomos,
which is how we came up with atom. So for a drawing of him, he just thinks you hit a point where there's something you can no longer divide. And that would be his idea of what an atom is. Dalton, many, many years later, about 1400 years later, he actually goes through and comes up with an atomic theory. So he's the one we're going to be talking about a lot. He has the 4 atomic postulates. So his atomic theory the 4 postulates are: all matter is made of atoms. And atoms are indivisible. So far he's the same as Democritus. His second one is that all atoms of one element, by this point they have discovered what elements are the same. He also said that compounds are combinations of 2 or more atoms. And that a chemical reaction is a rearrangement of atoms. Considering the fact that he came up with these 4 postulates based only on theories without actually being able to see an atom, it's very impressive that there are only 2 mistakes in this list of postulates. The first mistake is that atoms are indivisible. Atoms are made up of protons, neutrons, and electrons. He, of course, did not know that. He also said that all atoms of one element are the same, and in most cases they are the same in number of protons, and that's how we name an element. However, an isotope has a different number of neutrons, and an ion has a different number of electrons. But besides those 2 mistakes, the rest of these postulates are entirely correct. So a visual depiction of Dalton's model would just be a solid ball still. He doesn't know about anything included on the inside of the atom. He just knows that everything is made up of atoms. So J.J. Thomson is the first one to discover some of the parts inside of an atom. So what he did is he used a cathode ray tube. So if you think of your old TV, where it had that big tube in the back that would electrocute you if you touched it, that's a cathode ray tube. And he used it to find electrons. He figured out that there is something negatively charged inside of an atom. So what he did is if he took Dalton's idea of an atom and discovered that there's something negative in it. So his model is often called the plum pudding model because he just thought these negatives were randomly dispersed in a positive field. He knew overall it must be neutral. Ernest Rutherford is the one who actually figured out what this positive field would be. Ernest Rutherford used gold foil to find the nucleus. Found the positive nucleus. So we still have a round shape. We still have random negatives. We don't know where they're located. We just know that there are negatives around. But he found out that there's also a positive hard core
in the middle because when he blasted gold foil with alpha particles, many of them ricocheted back. So there was something positively charged and hard in the middle of these atoms. So Niels Bohr is the one who discovers the arrangement of these electrons, the arrangement of those negatives. So Niels Bohr finds the arrangement of electrons in orbitals. So now we have this positive core, but instead of negatives being randomly distributed about, we actually have rings where these negatives can be found. Negative, 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 negative. And James Chadwick is the one who discovered the last important part of the atom, the neutron. And the neutron, as you should know, is located in this center, these little zero charges. I'm going to go ahead and add that to this model. So you can redo it if you want, or just draw an arrow. The last thing we're going to discuss in this first video is light waves and frequency. So you know those electrons that Niels Bohr discovered that were in those orbitals? Well, sometimes those electrons jump orbitals, creating light waves and frequencies. The calculations involved with light waves and frequencies are very simple, especially because these equations and all of these units, what they are labeled for, are all in our equation sheet. If you want to flip to the back of your packet, page 37 and 38, those are the two equation sheets you'll be given on the AP test. So in order to calculate frequency, we have F, which equals frequency. C is a constant. It is the speed of light. So you just only plug in this number for C. That right there. And this little upside down Y, that's a lambda for wavelength. You're given a word problem that says the wavelength is this. What is the frequency? Plug in the speed of light and solve. To calculate energy, E stands for energy. H is Planck's constant, another constant. You always just plug in the given number. Right there. And F is the same, it's frequency. So if I gave you a wavelength, you could also get to energy by plugging into one equation, plugging that into the other equation. This is just a simple algebra skill. It's not often used in AP, but I do want to make sure to cover those two equations. And they are given to you with all of their constants and variables labeled. So if I was to look at a Bohr model of the electron, so I have these electrons in orbitals, if one of my electrons on these lower level were to jump, now how do I make it jump? Well, you have to add energy. So if I add energy, the electron jumps to a higher energy level. So I jump up here. Now, I haven't added enough energy for this electron to leave the atom. If I was to do that, then I'd be creating an ion, and that's a different situation. But I add enough energy so that it jumps in the air, like if I were to shock you. So since it doesn't have enough energy to leave the atom, and it's still attracted to this positive nucleus in the middle, it can't stay out here. Not enough energy to resist that positive nucleus. Not enough energy to stay at higher level. So it's going to
release that energy. So it falls down, releasing. It falls, releasing the added energy as light. So when you see light, what you're really seeing is just electrons leaping from where they are up, and when they fall, it's in this process of falling that light waves come out.